welcome to the U sub practice video. In this video we're going to get some good practice using the U substitution technique of integration. So just make sure you've seen the U sub concept video, which built up our concept, our definition of what U sub is, as well as the U sub part 2 video, in which we took a look at some of the rare exceptions for U sub. There are certain problems that it doesn't look like you can use our basic U sub to solve them, but you actually can. Alright, so let's start with this one right here. I'm thinking U sub, so I'm looking for something to make my U, my inner, and I'm looking for the derivative of that U, of that inner, to be elsewhere in the equation. So I'm looking for that, and I see that we have an x cubed right here, and I know derivative of x cubed is 3x squared. Well, here's an x squared, so this looks like something I could make my U, my inner, and in a sense, this x squared and this dx is the derivative of that inner. So this is a perfect integral to do a U sub technique on. So I choose my x cubed as my U, and the derivative of that U is 3x squared. Of course, I want to multiply both sides of this equation by dx. So I'm looking for a 3x squared times a dx somewhere else in this equation. Well, here's an x squared times a dx. I don't see a 3 though. Well, that's no problem. Of course, I can divide by 3 on both sides of this equation. And in a sense, that moves the 3 to the left side. So now, instead of having an x squared times a dx, which is this, I can just write 1/3 times du. So now I have this integral. And this isn't looking too bad. Of course, I'll take our 1/3, bring it outside the integral because it's a constant. And this integral is not too bad. I know that the antiderivative of e to the something, e to the u in this case, is just itself, e to the u. So I carry out that antiderivative, don't forget the plus c. And of course, now that I've gotten through that antiderivative, I'm going to get u's out of there and x's back in, because my initial integral question is in terms of x. So instead of writing u, I will write what u is, x cubed. And that's it for this one. So yeah, this type of problem is definitely one of your standard issue U substitution problems. When you're in your higher level engineering classes and you come across some antiderivative problems, your U subs won't be too bad. It's really easy to spot this U sub. I see something that could be a U, and I see the derivative, something that looks like the derivative of that U elsewhere in the equation. Standard U sub. So looking at this problem, I'm tempted to make this my U, because that looks like an inner. But U sub says I have to be able to find the derivative of that inner elsewhere in the equation. Well, what's the derivative of this inner here? The derivative of it is just 2. And I don't see a 2 elsewhere in this equation, but I'm not too worried about that because I always know that I can move constants to the left or to the right of that derivative equation as I need it. But how am I supposed to get this x out of here? That's the problem. The derivative of my u is just 2. There's no x's in here. So how am I supposed to get this x out and the du in, the derivative of that u? So this is one of those rare U sub exceptions. One in which I look at my problem and there's no u choice I can make such that the derivative of that u choice is elsewhere in the equation. But actually I can use U sub to solve this problem. And let's see how that goes. So I made my u choice. I substitute it into our integral equation, so there it is. But look, the derivative of that inside is just 2. And that will not allow me to substitute, get this x out of here, and du in. So the derivative of our u choice is not elsewhere in the equation, like I told you guys, like I taught you u sub. So again, one of the exceptions. But watch what happens here. I know I want to try to get all my x's out and u's in. I got to get this x out somehow. Well, this equation's not going to help me at all. It does not even have x in it. But this equation, my initial u choice, has x in it. Let me try to get x by itself. Alright? So, now that x is by itself, I can just write this guy instead of writing this x up here. And that's how I'm going to get this x out and u in. I don't use the derivative like I normally would, because the derivative of that u is not elsewhere in this equation. The weird thing is, I go back to my original u choice to help make it happen. Alright, so here's the state of my integral right now. I still got to get this dx out. Well, how do I do that? Well, I can use my derivative, because that has dx in it. So I multiply both sides by dx to get it in the numerator on the right hand side. And I don't see a 2 times the dx here. I just see a dx. Dx is by itself. So I'm going to divide both sides of this equation by 2 to essentially get it over to the left hand side and dx by itself. And now, instead of writing dx, I can just write 1/2 times du. And there we go. So now my u substitution is complete. I've gotten all my x's out, including the dx, and all my u's in, including the du. So now we just gotta carry out the algebra and see what happens. I'm going to start by getting this 1/2 and this 1/2 outside the integral expression because they are constants. So they join up outside the antiderivative to make a 1/4. Alright, so now I think I have to FOIL this u to the 8th inside here. And now I can antiderive each one of these terms using the inverse power rule. So antiderivative of u to the 9th is u to the 10th over 10, and antiderivative of 5u to the 8th is 5u to the 9th over 9. And of course, I want to plug x back in for these u's. So instead of saying u to the 10th, I say 2x plus 5 to the 10th, and etc. So be very careful. This is one of those exceptions to the way I taught you to think about u sub. Looking at this problem, we could not find the derivative of our u elsewhere in the equation. But you can still use the u sub technique on it. This is one of those rare exceptions. It doesn't occur very often, but I have seen it, and I bet your professor will test you on it. So this problem looks disgusting, but I'll choose my u as my natural log of t because I see the derivative of natural log of t elsewhere in my equation. Here it is. Here's 1 over t. That is the derivative of natural log. So this should be one of our standard u sub problems. So the derivative of this u is 1 over t. Of course, I want to multiply both sides by dt to get it in the numerator, because dt is in the numerator over here. And now I can put these into my integral equation. Of course, natural log of t becomes my u, and this 1 over t times dt will become my du. Okay, so the u sub is complete. All my t's are out and my u's are in. So what is the antiderivative of sine of u? Well, that's just going to be negative cosine of u plus c. And of course, instead of writing my u, I can write what u actually is. U is natural log of t. So here is my final answer. So this problem looks disgusting, but if you're scanning for a u and the derivative of that u, it's not too bad. This is one of my classic u sub problems. I see something that can be the u, and more importantly, I see the derivative of that u. Like, I wouldn't want to make my u sine of all this because the derivative of sine is going to be, cosine of some other stuff. And I definitely don't see a cosine here. So for this one, again, my standard u sub approach, I'm looking for something to make my inner, my u, and I've got to see the derivative of that u elsewhere in the equation. So I rewrite my problem because I don't really like this notation. Whenever I see that, I know it actually means this, secant of x, but the whole thing is cubed. So just be careful whenever you see something like that. People like writing the power in between the trig function and the argument. But it really means this. So the secant looks like an inside, so I might think of this as my u. And the derivative of secant is secant x times tangent x. So, the important step. Do I see the derivative of this u choice elsewhere in this equation? And at first, you may be tempted to think no, because this whole thing's going to be u to the third, and I just see a tangent x times a dx. Well, be careful. A secant x times a tangent x times a dx is actually in this equation. You've got to split this secant x to the third up like this. So now I have a secant x times a tangent x times a dx. So the derivative of this u choice is in the equation. It's just kind of hidden. So I'm going to go ahead with this u choice. I'm going to multiply both sides of my derivative equation by dx to get it in the numerator. So these two secants here will become u squared. And secant x times a tangent x times a dx, well, that'll just be my du. So it does in fact work out here. Yeah, you got to be very careful. You always have to try to split up your algebra and make those puzzle pieces work to your advantage, if you can. So from here is a simple inverse power rule antiderivative. And of course I can just put my u is equal to secant back in for u to get my final answer in terms of x. So this one's kind of tricky. Don't throw your u in right away. If we had done that, we would have gotten u cubed. And then we would have been wondering, what do we do with this spared tangent of x here? But before I put the u in, I split this secant x to the cubed into this. And now we're able to see our secant x times tangent x times dx. Alright, so I see this one. I'm looking for something to make my u. That looks promising. So the derivative of this would just be negative 3. But of course I don't see a negative 3 here. Well, that's okay. The derivative is negative 3. It's just a constant. And I know I can divide that and get it to the other side of my derivative equation to get dx by itself. Let me show you what I mean. So, derivative of my u, that's easy, negative 3. My dx is on the numerator, so of course I want to multiply both sides by dx to get it on the numerator. So now I have this. Well, I don't see a negative 3 times dx here. I just see a dx by itself. Well, no worries. I can just divide by negative 3 on both sides of my derivative equation to get that dx by itself. So now I can make this my u. And instead of writing dx here, I can just write 1/3 times du. Alright, so it looks like I was successfully able to get all my x's out and u's in. My u sub is complete, and now I just have to deal with this much simpler antiderivative. I'll take my 1/3 out, and the antiderivative of 1 over u is just going to be the natural log of u. And then I can just factor in my 1/3 and put my u is equal to 5 minus 3x in for this u. So my final answer is in terms of x. And that's the final answer. So that's it for the u sub practice video. Hope this allowed you to get some good practice with the u substitution technique of integration. Don't forget your u sub concept. U sub is the inverse of chain rule. You use it if you see something that looks like an inside, and more importantly, the derivative of that inside somewhere else in your equation. So 90% of the time when you see u sub integrals in physics or statics or dynamics or whatever class, they're going to look like this. It's really easy to spot the inner and the derivative of that inner. Inner could be x squared right here. What's the derivative of that inner? 2x. Well, here's x. Great. Do the u sub. In this case, this would be my inner. That'd be my u. Well, what's the derivative of radical x? Well, that's just a 1 over 2 times radical x. Well, here is a 1 over root x right there. There we go. Crunch the u sub. Right here, there's my u. What's the derivative of that u choice? Just 2x. Well, there's an x. Don't worry about these constants here. You can always just divide them over to the other side of that derivative equation over here, so you don't have to worry about that. But then you do have those very rare exceptions to this general u sub approach that I taught you. The derivative of your u, your inner, won't be elsewhere in the equation. Like in this case, if I choose this as my u, my derivative of it is just 2. It's no problem that there's no 2 here. I can just move that to the other side. But the problem is that how am I supposed to get this x out of here? So for these rare exceptions, you end up having to use your u choice twice. So once, you'll have to put it right in here. But you actually have to use it again to get that other x out. You would take this equation, solve for x, get x by itself, and then put it in there. So these are those weird exceptions, and they are quite rare, but they are out there.